Assalamu alaikum wa rahmatullah. Good morning, good afternoon, and good evening. Today we will continue our classes in formation evaluation, and we will talk about porosity. We have discussed this topic in the previous year, but we will highlight some of the aspects of porosity which will assist us to better understand the formation evaluation in general. So we know that there are many factors that actually affect the porosity, and on those factors are grains, packing, sorting, and grain size to some extent. When we talk about grain packing, which is the geometrical arrangement of the particles in the formation, we can have different arrangements. So, and based on the mathematical calculations, they found out that if we assume that the grain size is the same and the shape is also same, which is a sphere, the cubic arrangement can give us up to 47.6% porosity, while the triclinic arrangement can give us 26% porosity. So with different arrangement, of course, we will have different porosity values, and this is a theoretical calculations, because in reality it's almost impossible to find particles or grains which are similar in shape and size. So those values are theoretical values. Now let us see how we can find this value, the 47.6%, based on the mathematical calculations, and that will help us to understand the concept better. We know that porosity is equal to pore volume divided by the bulk volume. So, and in order to find the pore volume, which is equal to bulk volume minus matrix volume, so the bulk volume, which is the volume of the cube, and if we have this particle with 8 particles which are arranged in a cubic arrangement, if we slice it horizontally along the 3 edges, the 3 axes, we can end up with something like this. So here, in order to find the length of the edge, it's equal to 2r, which is the radius of the first sphere plus the radius of the second sphere. So, and we know that the volume is equal to the length of the edge to the power 3. So it's equal to r to the power 3, which is equal 8r to the power 3. And if we take a look at this diagram, we will find out that each particle of this is actually contributing of 1/8 of the whole volume. So 1/8 multiplied by 8 particles, which is the number of particles, will give us one sphere, and that means the sum of those parts will give us one sphere, which is the volume, and those representing the matrix. So to find the volume of the matrix is actually the volume of sphere, which is the outcome of adding all those parts together. So this is 4 by r cube divided by 3. This is the matrix volume. So by this we can say that we found out the pore volume. Now the next step is to supplement those values in the formula in order to get the final result. So if we substitute the bulk volume and the matrix volume divided by the bulk volume, you do the math, you will end up with 47.6%. So based on this concept, you can easily find the porosity value for any arrangement that you have. Now let us see how the bulk density is calculated. So we know that below the surface we have, it's either matrix or fluid. So and the density is equal to the density of the fluid, which is raw fluid, times the relative volume. And the relative volume, because those fluid will occupy only the pore spaces, so the relative volume for those fluid is actually the porosity, or the value of the porosity, plus density of the matrix, which is this one, times its relative volume. So if we have a unit or 1 and we subtract the pore spaces, whatever is remain is the matrix volume. So this is give us the matrix volume multiplied by the density of the matrix. And the fluid, we have it's either the hydrocarbon or the multifiltrate, and because the multifiltrate will occupy the embedded zone, so here in order to find the density of the fluid, we multiplied the density of multifiltrate by the saturation of the embedded zone plus the hydrocarbon saturation, and multiplied by 1 minus the saturation of the embedded zone, which is give us the hydrocarbon saturation in this case. Now this diagram will help us to better understand this formula, which is this one, which is the main formula for bulk density. As I said, we have it's either matrix or fluid, and we said that the fluid will occupy only the pore spaces. So the porosity, which is the volume related to the fluid, and fluid density is raw fluid. If we take the matrix, the volume of the matrix equal 1, and we subtract the pore spaces, whatever is remaining is the matrix multiplied by the raw matrix, which is the density of the matrix. Now by rearranging this formula, we can get the porosity value, which is equal the bulk density minus the raw matrix divided by the density of the fluid minus the density of the matrix. So this is the main formula for calculating the density porosity. We already know the fluid and we already know the matrix, and we can substitute the value from the density or the bulk density from the log, and then we can get the density porosity. Now we have talked about the log headers and the scales and how we can read it in previous lectures, so, and the arrangement as well. And we know that neutron and density are considered porosity logs, and they are always in the fourth track if we count the depth track. So this is 1, 2, 3, this is 4. So and each one have its own scale. So, but because both of them are in the same track, those two scale has to be consistent. So let's see, because before that, in some cases you can find that this is raw C, or you can sometimes find it raw B, which is bulk density. Rho is the density and B is stand for bulk. So the density, if it's in density, then you will find the scale is from 1.95 to 2.95. But if it's in density porosity, it will have the same scale as the neutron, from minus 15 to plus 45. So we have to take care and check what type of scale is used in order to not make mistakes when we are reading the values from the log. Now, always neutron and density are in limestone scale, and that's because we said we talked earlier about the calibration of the tools before it's used. It's being used in the field. It's usually being tested and calibrated to make sure that it's work properly. And this test is done on limestone, and there are some reasons. We will see why they choose limestone as a lithology for testing. But before that, there are some questions that come up. Why we put sandstone formation on limestone scale? Because they are reference. When we say in limestone scale, that means the readings in the log are referenced to the limestone, although it's been rated in different lithology, but with the reference to limestone. So it will read the sandstone porosity, but in the reference to limestone. The same thing, dolomite in limestone scale. It might, from the first look, it might look wrong, but there is benefit from that, and we will see. We will see it in a minute. Now we have some fact that neutron movement in sandstone is different from the neutron movement in limestone dolomite. That's absolutely right. That means we have three scales for the three different lithology. Now we cannot represent each lithology with its own scale in the log, so that's why we have to choose only one lithology to be used as a reference. And the reason why they choose limestone, because it's very stable and it has very low clay content. So that's for those reasons. For those two reasons, they choose limestone as a lithology reference. Now the density scale, as we said, that it has to be consist with the neutron scale because they are both in the same track. That's mean because neutron is always in limestone scale. That mean the density porosity equation has to be modified to be in limestone scale. And how we can do this modification is very simple, by substitute the value of raw matrix with the matrix of the limestone, which is 2.71. So we are assuming that our matrix is limestone by substituting the value of that matrix. sorry. And we have the fluid, we know which type of fluid there, and we can easily get the bulk density, so we can calculate the porosity. Now, what are the major lithology we encountered in reservoir? It's either sandstone, limestone, dolomite, or anhydrite, and each of which it has different density. Anhydrite is the maximum density that we can get. Now, as I said, neutron porosity is always in limestone scale. Because they are in the same track, they have to be in the limestone scale for consistency reasons. This is why we substitute raw matrix to be 2.71. So in the calibration is done in the water, so that means the fluid is equal to 1. So the raw fluid is equal to 1, which is the density of the water. So this is our equation. We have only one missing, which is the raw bulk, which we will read it from the log. Now, let's see how this consistency in the scale is being calculated, like why they put 1.95 for 0.47 or 45% porosity, and why they put 2.95, which is as an equivalent for minus 15 porosity. So we know that the maximum porosity that we can get is 47.6%, which is related to the cubic arrangement, as we already mentioned. But let us use 45 for simplicity, and we calculate the raw bulk, which the bulk density in this case. We will find that it's equal 1.95, which is this value. So the bulk density, which is equal to 0.45 or 45% porosity, is actually 1.95 gram centimeter cube, or gram centimeter cube. Now, for the other side, what is the maximum density we can get? As we said, it's for anhydrite is 2.98. Let's use 2.95 just for simplicity reason. We substitute that in our equation to get the porosity. We do the math, we can find that the porosity value, which is consistent with 2.95 sorry, this is 2.95, which is consist to 2.95 density, or 2.95 gram centimeter cube, is minus 15. So that is why we have minus 15 porosity, although we don't have minus 15 porosity in reality. But for the consistency reasons, to make those two scales consistent, we have to have this value minus 15. I hope it's clear. So now let's see the effect of using a limestone as a scale for the logs in our interpretation. We have 4 lithologies: dolomite, we have limestone, we have sand, we have lime, we have sand, we have clay, and we have gamma ray log, and we have density and neutron. This is our borehole. Now let us see how the logs will respond with those lithology. We have we assume that those three lithologies have the same porosity, which is 20 porosity unit, but they have different densities, of course. This is the gamma ray. We know that the gamma ray will be high opposite to the clay, but will be very low for sand, limestone, and dolomite. But now let us see how density and neutron will react. Before that, we said that neutron is always in limestone scale. So that's mean this 20% porosity that we encountered in sandstone, when we are trying to see how it's equal in limestone scale, we can easily use the neutron density cross plot. So we have those three lithologies. This is for sandstone, this is for limestone, and this is for dolomite, and those numbers are the porosity values that we have. So we simply know that the lithology is sand. We will go to this line, and the value of the porosity is 20, so that means it's here, and we draw a straight line down to intersect the limestone scale, and we will read the value, and whatever we get is the porosity values in limestone scale. So let us see. We draw a line, and we found out that the porosity value is 16.5 for sand. For limestone, of course, it will be the same value because we are using the same lithology. But for dolomite, we have 20. We draw a straight line to intersect, and we found that the porosity value is 27.5. So that means in limestone scale, the porosity value is underestimated for sand and overestimated for dolomite. That's mean we will always get a higher value in limestone scale for dolomite, and we'll get a lower porosity value in limestone scale for sandstone. Still, it might look wrong, but we will see that how we can benefit from all this at the end. Now, if we represent this in our log, we'll see that this is the 20% porosity we have. This is, as we said, 16.5% for sand. Of course, in limestone it will be the same, and it will be overestimated 27.5% for dolomite. Now let's come to the density. As we said that the porosity is the same, but they have different density values. We will use the density porosity equation, and we substitute. We already said that it is in limestone, so we will assume that the matrix is limestone, and we substitute with the values of 2.71 for the raw matrix. The fluid is 1, and we put the bulk density for each lithology of those, and we will get the density porosity. So those are the porosity values. We got 22.5% for sand. Of course, it will be the same for limestone. It will be less for dolomite. And if we take a look at this, it actually makes sense, since as with the increase of the density, of course, the porosity will decrease. So if we compare those two formations, the sand and dolomite, sand have lower density than dolomite, so it will have higher. Even comparing to limestone, it have lower density, so the porosity will be higher. And for dolomite, it has higher density, so the porosity will be less. So if we plot the values in the log, which is here, and we got this one. So now we got those crossovers. We see that the logs are crossing each other, and using those crossover we can identify the different type of lithology. So if we find that density is left, neutron is right, that's mean density is left, neutron is right, that's mean the formation is sand. If both are overlying, that's mean the formation is limestone. And if neutron is the left and density is the right, that mean the formation is dolomite. You might find it in some literature that it's positive, it's a negative separation for sandstone and positive separation for dolomite. And it's negative because the density value here is decreasing and the porosity value is decreasing, so it's negative, while we will see here that the porosity value is increasing and the density is also increasing according to the scale, so that's it's a positive separation for dolomite. Now based on that you can go through this and to find out the interpretation or test your understanding for that or whatever we have said earlier. This is also another example. You can go through it in order to understand it better. Now from the log here we have two porosity values as we see. For sand we have the neutron porosity, which is 16.5. We have the density porosity, which is 22.5. The same thing for dolomite. We have two porosity values, 12.5 density porosity and 27.5 neutron porosity. So how we know that which one is correct if we want to calculate porosity? Is it neutron or is it density? And it's simply we just sum both of them divided by 2 and we'll get the accurate value. So as I said, it might seem wrong at the beginning because we are getting values different than this one, but after combining both of them together we are actually getting the same value for the lithology, which is 20%. So that's mean those values, although they are different from the original values of the porosity in the formation, but it's very helpful in order to understand or to interpret the lithology, because as we can see here from the gamma ray, we can only differentiate between the gamma ray or the shell and the sand. We assume it's sand normally, but as we can see from the porosity log that this interval contains 3 different lithologies. It contains sand, lime, and dolomite. So this is how we use. So this is another example also how to get the average porosity for the 2 logs to get the accurate porosity value. Now let us see the effect of gas in the log response. When it comes to neutron log, we know that the principle of neutron is that it's sensitive to hydrogen, and since in gas the hydrogen content will be less, so that means the values or the porosity values in the neutron log in gas interval will be less. So if this is the original value in the gas zone, we will assume that we will find that the porosity values will be less. The same thing in limestone, it will get less. The same thing in dolomite, it will get less. Pay attention to the scale, it's decreasing in this direction, so all the values are actually decreasing. So these are the effect of gas in neutron. Now in density, the presence of gas in the formation will decrease the density, of course, because it will occupy the pore spaces and will reduce the density of the formation. So because it's decreasing the density, that means the density porosity will increase, because they are opposite to each other. As the density increase, the porosity will decrease, and as the density decrease, the porosity will increase. And since gas will decrease the density, so it will increase the porosity. So if we come to our density porosity values, we'll find that it's getting bigger, it will increase. The same thing for limestone, it will also increase, and for dolomite it will also increase. Increasing in this direction, the scale is increasing in this direction, and that is why if we substitute those values, because we said that it will decrease the density, and if the numerator is less, that means the value will be bigger, so that will increase the porosity value. This value will get bigger and will increase. So we can see that this separation is actually getting bigger than its normal. We have this separation in sandstone, the negative separation. It's now is getting more negative, and we have the positive separation in dolomite, which is reducing. It's getting less, because we said that it will decrease the density porosity, it will decrease the neutron density, or will increase the density porosity. So the separation in dolomite will decrease, while the separation in sands will increase, and in limestone will also increase. So this is how we can get, and we can know that this zone is a gas saturated zone. Now we'll see the effect of the clay in the effective porosity. So the effective porosity is equal to the total porosity minus the clay effect, and or in other words, it's porosity from the tool minus the clay effect, and the clay effect is equal to the volume of clay multiplied by the porosity of 100% clay. So if we substitute all those values, we can get that effective porosity equal to the porosity from the tool minus the volume of clay multiplied by porosity of 100% clay. Let's see an example. We have we want to calculate the effective porosity in this interval. So the reading of the porosity from the tool, which is in this zone, we will take the value of the two and the sum of the values of the neutron and density, and divide it by 2 to get the porosity from the tool, which is 35 porosity percent. And we will go to find the volume of clay. We will find it from this log, which is 0.4. We want to calculate the volume of clay in this interval. We can find it using this representation of sand versus shell. This is created by the software. You don't have to do it yourself, so and easily get the clay volume. So we can see from here to here, this is the clay volume in our in the point in which we want to calculate. So this is 0.4, this is the clay volume, and then we need to calculate the porosity at 100% clay. We will see in this log what is the zone of 100% clay. So this is the zone of 100% clay, and we calculate the porosity in this interval, which is the red arrow, and it's the mid way between, or the sum of the two divided by 2, and we will get the porosity at 100% clay, which is equal to 15%. Now, by substituting those values in the equation, we get that the effective porosity is 21%. See the difference that the effect of the clay in the porosity is actually reducing the porosity. It was 35%, but due to the presence of the clay in the formation, it's now reduced to 21%. This the diagram will help you to better understand the log response in different lithologies. So we can see that, for example, if we have 20% porosity limestone, and the limestone is fully saturated with water, it will give us the exact porosity of that limestone, which is the 20% here. Shell is indicated by high gamma ray and high neutron porosity, because it's contain water, and the water contain hydrogen, and that's why it will the neutron log is sensitive to hydrogen, so it will give us a high porosity in shell. So this is one of the indicators of shell. This is 20% sand, 20% porosity sand, and the sand is saturated with water. It will show a lower porosity. It's almost 15, because as we said, it's in limestone scale, and will give us less values. Now we have this, for example, dolomite. It has 0% porosity, but as we also mentioned that the neutron is in limestone scale, will give us overestimate the porosity. It will give us almost 5% porosity, and so on. So you can go through the diagram and you will better understand the response of the neutron comparing to either water saturation or any other aspect. This is also another example as well, the response of the neutron and density, the crossovers in shell, the neutron to the left, density to the right. You might be noticed that the response of the neutron and density in shell is similar to that one in dolomite. So in this case, to differentiate between the shell and dolomite is by using the gamma ray. We will see a high gamma ray value in the shell interval, will be low gamma ray in dolomite. In limestone, neutron and density will more or less coincide with each other. This is the negative separation in sand, positive separation in shell. We have also positive separation in dolomite, but in this case the gamma ray is the one we should differentiate between limestone and dolomite. Now in in some cases we can find that the porosity values might reach more than 47%, and this is due to, it can be due to the bad borehole environment, because if we have cavings in the borehole, this is the caliber log, we have cavings in the borehole, and those caves are filled with drilling fluid which is containing hydrocarbon, containing water hydrogen atoms, and that's the neutron log will read more hydrogen, and that will translate that into porosity, so it will give us higher porosity. So if we saw the caving in this zone and the caving in this zone, the increase of the caving, the porosity value is also increasing. Although the gamma ray is also higher, it's increasing the same way the caving increase the porosity readings at the end. Now the log header, I guess we will stop here and we will continue from here to in the next lecture.